So here we want to look at some examples of sequences that may not have a very simple formula that describes each term of the sequence. And the first example looks at the sequence Pn, where Pn is the population of the world as of January 1st in the year n. And so, of course, Pn would be something that we would probably don't even have exact values for, because maybe these are numbers that we don't necessarily even know exactly what they are. We can of course approximate them and use various census data and things like that to construct an approximation for these values. But of course these numbers are going back to the year 1 may not even be something we can find an exact value for. In B, we let an be the digit in the nth decimal place of the number e. So so remember, e, of course, is this irrational number that has an infinite decimal expansion that doesn't repeat and doesn't terminate. So we can imagine that those decimals there form their own sequence. In this case, 7, 1, 8, 2, 8, 1, 8, 2, 8, 4, 5, and so on. So you see that itself is a sequence. You can also do the same thing with, say, any irrational number, like pi, for instance. You can do the same thing, and so on. So, you can define a sequence here that gives me just the decimals of pi. Okay. And these ones are definitely ones that we can determine. They're able to be determined, but maybe there's not a very simple formula that would generate these terms for us. Fibonacci sequence is a very famous example of a sequence that can be very easily defined, but in a recursive way. So the way we're thinking about a recursive definition, in this case for the Fibonacci sequence, is where we give a value for the first term. In this case we say f1 is 1, and the second term in this case is also 1. And then we give a way of generating from those first two terms all the terms that come after it. So for instance, to find now the third term of the sequence, we say fn is defined as the sum of fn minus 1 and fn minus 2. In other words, it's the sum of the two terms that came before it. So in this case, we know the first term is 1, the second term is 1. So now to generate the third term, we'll take the sum of 1 plus 1, and that'll give us the third term. To get the fourth term, then I'll take the sum of the two terms that came before it, 1 plus 2, give me 3. And then to generate the fifth term, we'll take the sum of 2 plus 3 to give me 5. And so on. So you can continue this pattern. 3 plus 5 gives me the next term 8. 5 plus 8 gives me the next term 13. And so on, right? So this can continue forever, and you can generate subsequent terms of the sequence very easily just by summing the two terms that came before it. All right, so in this case, what we're giving you is a recursive definition. So to get a more explicit definition, we would want a formula where I can just plug in the value of n, and it would give me a way of computing the nth term directly. In this case, if I want to, for instance, get the 100th term of the sequence, the way we've defined it here, I would have to go through all 99 terms that came before it, and then I would be able to generate the 100th term. Okay, so you see that this is recursively defined because it relies on the terms that came before it. To picture a sequence, oftentimes we can imagine it as, for instance, here our sequence an equals n plus 1. We can imagine it as a succession of points on a number line. Where here a1, right, would be the sequence here starting at 1 would be 1/2. a2 would be 2/3. a3 would be 3/4. a4 would be 4/5, and so on. And we can kind of see here that a1 would land there at 1/2. a2, which is 2/3, would land there at 2/3 on this number line, somewhere in between 0 and 1. 2/3 lands right about there. 3/4 would be where a3 lands. 4/5 is where a4 lands, and so on. You can continue. The ticks here would, of course, appear to get more and more cluttered as the sequence progresses. So in other words, the values are harder to distinguish when the sequence progresses further. So maybe there's a better way to look at it, and here we're kind of graphing it more like a traditional function where we're graphing it in the xy plane, where each term of the sequence corresponds to a point in the xy plane. Thinking of a1 would be the value at 1, a2 would be the value at 2, a3 would be the value of 3, and so on. So we can kind of think of it this way, right? It's more like graphing the function x over x plus 1, but rather than putting in all the values for x, we're just putting in the integer values. And so we get a sequence of discrete points in the xy plane. And this is perhaps better than this graph here, because as the sequence progresses, we can kind of see how those various points will be distributed. And what it appears like in the picture as the sequence progresses, we seem to be getting closer and closer to this line at 1. So we can imagine here 1 is really like our horizontal asymptote. And so we can imagine what's really happening here is that the limit as n goes to infinity of the sequence is equal to 1. And we can actually work this out. We have the nth term formula is n over n plus 1. And I can manipulate this a little bit. If I divide n to the top and the bottom, I get 1 over 1 plus 1 over n. And we see as n goes to infinity, 1 over n goes to 0. So this becomes 1. And so our limit here appears to be approaching this line at 1, because each of these terms of the sequence gets closer and closer to 1, and eventually they'll be very, very close to 1.